Next talk, so I'd like to introduce Alexander Dragojevic, who's a researcher in our systems and networking group. So Alexander is going to share his research about transactions and his teamwork.
Yes, thank you for the introduction. Today I'm going to talk about distributed transactions for modern data center hardware. This is joint work with several of my colleagues here in Systems Networking Group in Cambridge, and also with several other people in other parts of the company. I just wanted to mention that if you have any questions, please do not hesitate to interrupt and ask them as you have them. Okay. So as most of you know, distributed transactions are really powerful primitive. They provide a very nice high-level abstraction of a distributed system. Basically, they represent the whole distributed system as a single machine that never fails and executes transactions one after another. And this means that it hides all the details of concurrency and failures which make distributed systems hard. So building or using distributed transactions really significantly simplifies using a distributed system. Unfortunately, distributed transactions are believed to have poor performance, and that's why they're not very widely used in systems deployed in data centers. So these systems either do not expose transactions at all, or they expose some weaker form of transactions, for instance, eventually consistent transactions, or transactions that are only allowed to access data in a single partition of data, or something like that, which then again makes it harder to use a distributed system. And in this work, we basically show that things do not have to be like that. We show that you can have distributed transactions with strong consistency, very good performance, and high availability. Okay? So to do this, we basically rely on several hardware trends that are making their way into data centers. The first one is having large amounts of main memory in commodity servers in data centers. So servers today already have 256 gigabytes of DRAM, so basically commodity servers. And this means that a small cluster of several tens of these servers already has enough main memory to store entire data sets of many interesting applications. The second trend that we are relying on is this move towards non-volatile memory. You probably all heard about Intel announcing and Micron announcing their non-volatile memory technology. But in the meantime, while we are waiting for it, we basically can build non-volatile memory out of DRAM, a battery integrated with the power supply of the server, and using this battery to flush the contents of DRAM to SSD when the power goes away. So in this way, basically get non-volatile memory already with technologies available today. And the third trend we are using are these really fast networks that are being deployed in data centers. So these are networks like InfiniBand and Rocky, if you're familiar with these, but basically they have very high bandwidth. So today it's possible to buy a NIC with 100 gigabits of bandwidth available. Very low latency, only 1 to 3 microseconds is the lowest latency, and also they support very high operation rates. So we can see 100 million IOPS per second with these NICs. And in addition, they also support RDMA. RDMA stands for Remote Direct Memory Access, and I'll describe in a bit more detail what this means. But this basically gives us an opportunity to even further improve performance. And so what is common, what do these three hardware trends mean for people building systems for modern data center hardware? Basically, if you look at them, they are removing the bottlenecks, the networking and storage bottlenecks, which are the traditional bottlenecks we have in these kinds of systems, and they are exposing and leaving the CPU as the main remaining bottleneck. So just to illustrate what this means, I did this back-of-the-envelope calculation. I took one of the latest Intel CPUs, which has 18 cores and 3.3 gigahertz maximum frequency, and again the latest NIC, which supports 100 million one-sided operations per second. And if you assume a server with 2 sockets, this means that we roughly have just above 1,000 cycles per each of these one-sided operations. But keep in mind that actually to issue a single RDMA operation, we need to spend actually more than 1,000 cycles. And this means that a system that is only issuing RDMA operations is already CPU bound. So basically, the CPU here is the bottleneck. There are no CPU cycles left to perform any useful application work. So in order basically to use these hardware trends that we have in the system, we need to optimize for the CPU. And this means that even though we could deploy existing systems on this new hardware and they would run faster just because the hardware is faster, right? To fully exploit this new hardware, we need to design systems from first principles, keeping in mind the characteristics of the new hardware. And in this work, this is what we do for transaction recovery protocols. We basically build them to minimize the CPU overheads. And while building these protocols, we follow these three design principles. One is to use one-sided RDMA operations. This helps us not only improve performance because they're more performant than exchanging messages over RDMA, but also to reduce CPU overheads because they're more CPU efficient than sending and receiving messages. We also design protocols to reduce message counts. So for instance, our transactional protocol has transactional commit protocol has 4 phases instead of 2, like more traditional 2-phase commit and similar protocols. And I'll explain later why this is a good idea. And also we aim to effectively use parallelism because obviously these systems that we have today are very highly parallel. So we have tens of cores in commodity servers. So in order to use the hardware efficiently, we need to use this parallelism effectively. And I'll also later give some examples of what this means in our design. Okay, so in the rest of the talk, I'm going to provide a little bit of a background about the system that we are building here, and then I'm going to talk about transactional recovery protocol, and then I'm going to show some evaluation results. So this work is part of this FARM project. FARM stands for Fast Remote Memory, and this is a project that is building a distributed computing platform with the goal of enabling to build key value stores, graph stores, OLTP databases, and similar systems on top of this system, on top of this distributed computing platform in an easy way. So FARM keeps all data in main memory, uses RDMA extensively. It represents the memory of all the machines in a cluster as a shared address space. The applications are written to FARM API, and we expect to have applications, and the applications basically can use transactions as the main primitive. So these transactions can read, write, allocate, and deallocate objects in this shared address space. Okay? And so we expect these objects to be fairly small, tens to hundreds of bytes, because of the applications that we are aiming to support. And these are the applications that are going to benefit the most out of the system that supports this random accesses and low latency. Okay? So when I talk about transactions, I talk about transactions in this setting. Although I believe that the techniques can be used in other cases too. Okay? So how does the FARM use this machine in a cluster? Basically, I mentioned that it takes the memory of all the machines and exposes them as a shared address space. So every machine takes most of its memory and contributes it to this shared address space. And this is done in these chunks of 2 gigabytes that we call regions. And then FARM extensively uses RDMA to access these regions. So we use RDMA read to read objects in memory of remote machines. So to do this, a machine that wants to read an object sends a request to the NIC of the machine that has the data. The NIC then performs a DMA directly from the memory and sends back the resulting data to the machine that issued the request. So notice that the CPU is not involved in this operation at all. And also, we make sure that the objects that are read are consistent. I won't have time to talk about this, but there are more details in a paper we published. Oops. At NSDI a few years ago. Sorry about that one. Also, FARM uses RDMA writes to implement efficient messaging. The idea is basically to expose circular buffers in memory of a receiver, and then messages can be written to this circular buffer using RDMA RDMA writes. And there's going to be a single circular buffer for every possible sender. And so to send the message, basically the machine again does an RDMA write. The NIC stores the data using a DMA operation, but obviously in order to process this message, the CPU on the receiver side needs to poll the channel, see the message, and then process the message. But note that in this case, basically the NIC is going to send a hardware level acknowledgement. So this means that the sender knows that the message is being stored in the memory of the receiver safely, even before it is processed by the CPU. And this can be used to optimize the protocols a little bit, and I'll show you how in a few slides. Another thing to note here is that these circular buffers live in persistent memory, so in non-volatile memory, so they can be used as persistent transactional logs, and this is what we do. Okay, so this is how Farm uses RDMA. A little bit of background on it, and next I'm going to talk about transactions. One of the main goals when designing these transactions in Farm was to achieve high performance. Obviously, I mentioned that distributed transactions are believed to have poor performance, and if they perform poorly, people basically do not want to use them. So we tried really hard to achieve good performance. So Farm uses one-sided operations, as I mentioned already, to read objects and to log updates. And we also designed our protocols to reduce message counts because issuing and processing messages takes up CPU. So sending fewer messages actually reduces the CPU overheads. And to do this, we basically use a primary backup replication instead of a quorum-based or Paxos-like replication because this requires sending replication messages to fewer backups. And also we are in the data center settings, so the latencies are not as highly varying as they are in a wide area network. So this is a good choice. We also use optimistic concurrency control. But for instance, you do log reads without acquiring logs, which again reduces the number of messages because we do not need to send messages to acquire and then release the logs later. And we also allow accesses only on the primaries because this means we do not have to lock objects on the backups, and again reduces the number of messages we have to send in the protocol. So as I mentioned, the applications in Farm are basically written to use transactions, and this is the main primitive that they use. Each transaction is executed by a single thread, which is the coordinator thread. In this case, I denote it by letter C. But then in the system, there are going to be many transactions executed at the same time by all the threads that we have in a cluster. And transactions are fully general distributed transactions, so the coordinator transaction can read any number of objects on any machine in the cluster. And these reads are done using one-sided RDMA read operations. Writes are buffered. They're also performed optimistically, so as the transaction executes and performs some updates on the objects, the updates are buffered in the local memory, and they're not exposed to the other machines in the cluster until the transaction commits. Once all the operations are performed by the transaction, it enters the commit protocol and attempts to commit the transaction. If the commit succeeds, all the updates become atomically visible to the rest of the cluster. If it fails, then none of them are visible to any other thread in the system. And typically, the coordinator then retries the transaction and attempting to commit it later on. So how does Farm commit transactions? One possible option is to use a two-phase commit protocol, which is a very well-known protocol where the coordinator would send the messages to the primaries, here P1 and P2 on this slide, and then they would send it to the backups, and the messages would then go back all the way to the coordinator. And this would work fine. We'll be able to commit the transaction in only 2 round trips, but this uses quite a few messages, as you can see, and also all these messages need to be processed by the CPU. So for these reasons, we decided to design our own protocol to minimize the number of messages and the CPU processing. And this is what the Farm protocol looks like. So the first step in the protocol is for the coordinator to attempt to acquire the logs of all the objects that have been written by the transactions. This is done by sending messages to the primaries of these objects. The messages contain the contents of the new contents of the object, and they also act as a log. They are stored in these persistent non-volatile circular buffers. Then the primaries attempt to acquire the logs. They do this by using local compare and swap instructions. Basically, each object has a version associated with it, and they attempt to acquire the log from the version at which the object was read during the execution. If all the logs are acquired, the coordinator proceeds to validate the read set. Validating the read set means reading the versions of the object that have been read but not written in the transaction, and this is needed to ensure that the objects haven't changed since they were read during the execution of the transaction. If validation succeeds, if none of the versions have changed, then the transaction can proceed to replicate the logs. This is done by issuing one-sided RDMA writes to the backups of the objects that are updated by a transaction. And the coordinator does not need to wait for these messages to be processed by the CPU. It basically can proceed as soon as it receives this hardware level acknowledgement sent by the NIC. And yeah.
So you said that your approach to concurrency is optimistic. What would be the opposite of that? I like the standard way of doing it.
Well, pessimistic would be to basically acquire the logs. So depending on how pessimistic you want to be, you could acquire the logs, for instance, only for the objects that are being read, but you could also acquire the logs as soon as you read or write the objects in the execution phase of the transaction. Yeah.
Do you validate both primaries, or is it just you've only got arrows for P1?
Yeah, so this is just because it's just an example. So basically, the example assumes that the only object that was read but not written lives on P1. So we basically validate all the objects that have been read but not written. Okay. Okay, and so the final step is after replication is to update and unlock the objects on primaries, and this is done by writing commit log entries into the logs on the primaries. Again, the coordinator does not have to wait for the messages actually to be processed. As soon as it receives X, hardware level X from the network, it can basically report the transaction as committed to the client code. Of course, these messages here are going to be processed soon by the primaries, and only after they are processed, the objects actually get unlocked and the contents of the objects get copied into the main memory and can be accessed. The new contents can be accessed by other machines. These log messages get processed when the transaction is truncated. Transactions are truncated lazily in a batch manner, and all the truncated messages are basically truncated records are piggybacked on the other messages in the protocol. So this is done quite efficiently. Okay, and so this is what the protocol looks like. And what you can see is that we use a lot fewer messages than we would if we used the two-phase commit protocol. But you can also see, which is good, but you can also see that we have 4 phases, unlike two-phase commit protocol, which has only 2. But one thing to note here is that the latency of the transaction is not going to be significantly impacted by these phases, because only in the first phase, only in the log phase, we need actually to wait for the CPUs on the receiving machines to perform any action, which is the operation that is actually going to cost us the most latency. In the other cases, we essentially wait only for the hardware level X and proceed immediately after that, which reduces the latency. So the impact on the latency is not as high as you might think. Okay? Any questions? Okay. So this is how farm commits transactions when there are no failures. Next, I'm going to talk about failure recovery. I already mentioned that we use one-sided operation. Farm uses one-sided operations to improve performance, but this actually complicates failure recovery. And the main reason is that with one-sided operations, we do not have the CPU on the remote end to actually process these messages. So in traditional systems, for instance, the CPU can reject messages when a machine gets kicked out of the system, which simplifies failure recovery. when using one-sided RDMA operations, this is not possible. Using one-sided operations actually impacts the way we do the configuration change protocol. We require precise membership, and I'll mention what this means. This is because of using one-sided RDMA operations, and it also impacts recovery because, for instance, we need to drain messages of logs before recovering because there are some of the messages that haven't been processed yet by the primaries and backups, but already the transactions were committed and reported committed to the client. Okay, and so while designing this recovery protocols, we basically aim to achieve high availability. So we use this primary backup system, which means that we are going to have some downtime when the machine fails and as the cluster agrees on the new membership of the cluster, but we would like to keep this downtime as short as possible. What helps us with this is that we keep both primaries and backups in main memory, and this means that all the data is available in main memory as soon as we recover from the failure. So if a backup is promoted to a primary, the data is already going to be there. We won't have to recover it from a disk or something like that. We also made sure that we achieve very short failure detection times. We were basically able to detect failures in 10 milliseconds by carefully engineering our failure detection, our failure detectors. This is actually quite low because most systems typically use much higher failure detection times, seconds or even tens of seconds, because of all the uncertainty you have in the system. And we also use parallelism as much as we can, again, to make the unavailability time as short as possible. So for instance, we do not block the new transactions or we avoid blocking the new transactions during recovery as much as we can. We also recover transactions in parallel and recover data in parallel to shorten the recovery time. So what does recovery look like? From a high level, it looks like recovery in any similar system. So we first need to detect a failure, then we have to change the configuration, then recover transactions and recover the data. And in the next few slides, I'm going to briefly describe each of these steps. So we detect failures by exchanging heartbeat messages, leases between machines in the system. So in a cluster, one of the machines is going to have a role of a configuration manager. So in addition to executing client code and committing transaction, it also has some other duties, and one of them is to exchange leases with all the other machines in the cluster. And this means that this configuration manager is its responsibility is to detect failures of other machines, and at the same time, all the other machines detect failures of the configuration manager. So when a machine goes down, it won't be able to respond to the heartbeat messages by the CM, and it's going to get kicked out from the configuration. After determining the new configuration, the configuration manager writes the new configuration into the Zookeeper. And Zookeeper is basically this service that provides agreement, and we use it in this vertical Paxos manner and basically use it to agree on what the new configuration is. For instance, when the system starts up, or when the CM fails, there are going to be multiple machines that are going to attempt to become the new CM, and then having this service is useful because they can go there and do this. Okay. So I mentioned also already that we need fast failure detection, obviously, to recover from failures, in a short period of time. So we use 10 millisecond timeouts, which is a lot shorter than other systems. And the goal when implementing a failure detector is to have as short failure detection time as possible, but also to have as few false positives as you can, because every false positive is going to be quite expensive, as it will require going through all the recovery steps. And the problem here is that any interference can lead to these false positives. For instance, scheduling quantum on Windows is 100 milliseconds, and also the latency of a traditional network can be much higher than 10 milliseconds. Luckily, we have a fast network, and by removing the interference at all levels of the system stack, we are able to achieve these short failure detection times. So we use a dedicated high priority thread, we use dedicated network queues, we pre-allocate all the memory needed for the failure detection. We also use log-free data structure when exchanging messages and talking with other threads in the system. Yeah.
What percentage of false positives do those last few steps eliminate? I mean, do you still get some problems when the high priority isn't enough?
So we were able in our experiments to get no false positives with 10 milliseconds. But this really depends, right? You can be a bit more aggressive and actually use 5 milliseconds, even shorter leases, in which case, when you would have more false positives, right? Or you can be more conservative and just set it to higher value just in case. Yeah. There are some details about exactly how much each of these steps contributes in the paper. I'm not going to show them here, but all very important. So after the failure is detected, as I mentioned, the configuration manager is going first to determine what the new membership or the configuration of the cluster is, and to do this, it performs this probe step. This means that it issues RDMA reads to all the candidate servers for the new configuration, and it takes all the servers and puts them in the new. All the servers that respond go into the new configuration. The reason for having this probe phase is really to optimize for correlated failure. So for sometimes a whole rack of machines is going to go down because top of the rack switch stops working, or there's a problem with the power supply for the whole rack. And if you just rely on leases, this might actually mean that we'll have multiple configuration changes because only one of the leases is going to expire, like one of the heartbeats is going to get lost or be noticed missing. And so for this reason, we do this probe phase just to deal with these and fewer configuration changes. Then the next step, as I mentioned, is to write the configuration to the zookeeper. At the same time, the configuration manager is going to remap regions. Right now, we lost a few machines, and this means that some backups and primaries of some regions are missing. So they need to be assigned to the remaining machines in the cluster. And while doing this, we aim to, again, reduce the unavailability time. So as I already mentioned, the backups become primary, so the data is available very shortly after the failure. And also we balance the new backups around the cluster to make data recovery and transaction recovery faster, basically allow doing it in parallel across more machines. After the configuration is written to the zookeeper, the next step is to send the config new message to all servers in the new configuration. And at this point, after receiving this message, every server stops processing messages or stop processing the regions that have been impacted by the configuration change. The processing for all the other regions basically keeps happening as usually. Then the servers send a config ACK message back to the configuration manager, and after receiving all config ACKs, the CM is going to send config commit messages to all to all servers in the new configuration. And at this point, we start recovery. So the reason why we need this three-way handshake that you see here, we need it because we use one-sided RDMA reads, and we want to avoid starting recovery while some servers in the configuration, while some servers might still think that they are in the old configuration. So at this point, when we receive this config commit message, basically each server knows not only about the new configuration, but it also knows that every other server in the configuration knows about it. So it is not going to be incorrectly reading data. It has already stopped processing these regions that need recovery. Okay, and so this basically gives us this precise membership, and this is one of the impacts of using one-sided operations. Okay, next the system is going to perform transaction recovery. Transaction recovery is done on a per region basis, basically for all the regions in parallel. Before going to recovery, all the servers actually first need to drain their message logs. And the reason, and when they do, what they do is basically they process all the messages that are there, and that have, and that the coordinators of some transactions already have considered processed because they received network hacks. And then at this point, they basically stop processing the messaging from the old configuration from now on. And this is needed because in case we have more failures and more configuration changes, we would like to have the set of messages accepted from a configuration be the same, or otherwise we might decide to commit transactions that we decided to be aborted before. Okay, and so the first phase of transaction recovery is first to find all transactions that need recovering, and this is done by all the backups finding transactions in their logs that require recovery and sending them to the primary. At that point, the primary can acquire the logs for all the transactions that are being executed that need recovery. And notice that at this point, basically, the primaries are all going to have all the data in main memory, and they're also going to have acquired all the logs for the transactions that need recovering. So basically, all the regions are in the same state as they were before the failure. And so this means that the machines can now start again accessing the regions that have been impacted by the failure. And from this point on, the foreground operations are going to be performed in parallel with recovery. And this significantly reduces the downtime. So remember, the regions were not being accessed only from the time the config new message was received until the logs are successfully acquired. The next step is to replicate the logs. The primary basically replicates the logs, so the logs are again replicated 3 times just in case there are more failures. And then it sends the vote to the coordinator. If the coordinator has not failed, the coordinator remains the same and we send the vote to the old coordinator. But if the coordinator has failed, then the machines pick the coordinator in a consistent way, but in a way that spreads again the load of transaction recovery by spreading the coordinators around the cluster. And after the coordinator receives the vote messages for all the regions involved in a transaction, it's going to send a decision message to all the participants, and then the transaction either gets aborted or committed. And this is basically how Farm recovers transactions. I know that this is quite involved and there are quite a few steps, but if you would like more details, you can have a look at the paper and we can talk later. You can ask questions now. But a few important things to remember is that we basically do recovery in parallel for all the regions that are there in the system, and we also block foreground operations for a very short period of time, and only for the regions that are impacted by the failure. So basically, between receiving config new message and reacquiring the logs, there's no processing of these regions. Okay. So in addition to recovering transactions, the data also needs to be recovered, and we parallelize this data replication. So we basically need to recreate backups for the regions that have lost backups. And this is done again in parallel. To speed it up, we balance replicas around the cluster as much as we can, which is similar to a system like RAM cloud, and this is a technique that's well known to reduce the downtime or to speed up recovery. Big difference to RAM cloud is actually that we do not have to wait for the data to be read off the disks. Data is already there in main memory, so it becomes available much sooner. This also means that we can do data recovery in the background, so basically to avoid interference with the foreground traffic and with the rest of the recovery. So we start data replication only after logs have been acquired, so to reduce at all primaries, this is to reduce the interference with acquiring the logs, and we also pace it in the background in order to reduce the impact on the foreground traffic. Okay. So if there are no questions, I'm going to next show you a few results from our evaluation. To evaluate the system, we use the cluster with 90 machines. Each machine has 2 56 gigabit NICs, 32 hardware threads, and 256 gigabytes of DRAM. We used standard OLTP benchmarks, TATP and TPCC, and then in the evaluation, we wanted to see what the performance of the system is and how fast we can recover from failures. So first I'm showing a throughput latency curve for TATP. the x-axis shows throughput in millions of transactions per second, and the y-axis shows latency in microseconds. I'm showing two curves, a median latency, 99 percentile latency. And as you can see, performance is really high. We were able to perform 140 million operations per second with a median latency of only 60 microseconds. And at the knee of the curve, the latency is actually halved with only a moderate impact on throughput. And also, the 99 percentile latency is quite good. It's less than 1 millisecond, which is, for instance, comparable to the latency of a single TCP message exchange in a loaded system. Okay. We also ran the same experiments for TPCC. Here is the throughput latency curve. The throughput shows million TPMC, which is the performance metric for TPCC, in millions, and the y-axis shows latency in milliseconds. Again, TPCC has much bigger transactions, so the latency is higher. It is now full milliseconds. And again, the throughput and latency are really good, 270 million TPMC at 0.8 milliseconds. And again, the latency is almost halved by only sacrificing a little bit of throughput. And this is really good performance. If you're not familiar with TPCC, I can tell you that a database person I talked with initially thought that I meant thousands instead of millions when I was talking about TPCC performance. Okay, an interesting comparison to make when scaling out OLTPs to compare to a performance of a single machine. Scaling out OLTPs traditionally very hard because of all the overheads of the network, of networking that are required for scale out. And what happens often is that a scale out system requires several machines or even tens of machines to recover the performance of a single tuned single machine system. This is not the case with Farm. I'm showing here a comparison with Hackathon, which is SQL Server's in-memory component. This is comparing to the Hackathon engine. This is basically, Hackathon has no fault tolerance, obviously, with a single machine. The logging was turned off. And Farm has fault tolerance by using three-way replication. And with a system with 90 machines, we are basically able to store 30 times as much data as a single Hackathon instance and achieve 20 times higher throughput. Just to zoom in to show that we basically have almost the same performance already as we run with 3 machines, which is the fewest machines we can run with if we want three-way replication. Okay? So next I'm going to show you how the system performs or behaves when there are failures. Here I'm showing the performance over time. So the x-axis shows time as it passes, and the y-axis shows throughput in again millions of operations per second. In this particular experiment, we kill a single machine at time 0 here, and then see how long it takes before the throughput recovers all the way to where it was before the failure. And as you can see, it takes only about 50 milliseconds to recover the throughput to where it was before the failure, which is quite good, comparable or actually lower than the latency of a single operation in many other systems. So of course you might think, yeah.
I have a question about the performance numbers.
Yeah.
So there's some assumption about congestion on the logs, like what would happen if more transactions try to modify the same object?
Yes, so this is basically a TATP benchmark, which is a standard benchmark that we took and then we ran. If more transactions attempt to acquire the same lock, if there was more contention, the performance would be lower. Obviously, with a different workload, the performance might be lower, and we might have to use some techniques for dealing with this. What we do right now is we basically use a randomized backoff to deal with contention, but we could do things like delegating, committing of transactions for a particular object to the same machine, or using flat combining. Actually, in a our NSDI paper, we describe how we use flat combining on hash table and YCSB highly contended workload. Yeah.
The last one you said it scaled up to like 90 servers.
Yes.
Is that, how many racks is that? And do things change when you go cross rack or?
Yeah, this was, in this particular case, we were running with a single big switch, if that's what you're asking, and we had, I don't know, it doesn't really matter how many racks we packed it in, but this was a single big switch. We also ran it in other configurations across multiple switches. We don't really have a comparison because this was a production environment, and comparison might not necessarily be fair because there were many other things going on. But actually, this scales to many racks, or should scale to many racks. We tried with a handful. Okay. So next I'm going to show you the distribution of recovery times. This is just if anyone's thinking that the previous graph was sort of carefully picked to show the best recovery time. And actually it was very close to the median recovery time. What I did is I ran a bunch of experiments and then measured how long it took from the point in time the machine gets inspected until we get back 80% of the throughputs we had before the failure, and you can see that the median number here is 26 milliseconds, and actually the maximum is around 200 milliseconds. So recovery is fast in more than one graph. This graph basically, again, is the same experiment, TATP failing a single machine, and this shows how fast we actually re-replicate the data. This is basically the same experiment, just zooming out. The red line shows how many of these 2 gigabit regions we recovered up until a particular point in time. And you can see that it takes about 33 seconds to recover about 160 gigabytes of data without impacting the throughput of the system. You're of course wondering what these dips are, and I can tell you that these also happen when there are no failures. We believe that they're because of basically intervals of high contention for particular objects in TATP. Okay, but we recover the data in a short period of time again without impacting throughput at all. And one final graph to show is basically what happens when we fail more than a single machine. So in this particular case, we fail 18 machines. So this is 20% of the machines in the cluster, and this is simulating a failure of one of the racks in a system. So as I already mentioned, all the machines in the rack might fail together because of a power failure or because of top of the rack switch failure. To deal with these cases, farm supports this notion of failure domains. So basically all the machines that can fail together are put in the same failure domain, and so multiple replicas of the same region are not going to be put in a single failure domain. So even if the whole failure domain goes away, we still do not lose data. And in this particular case, as you can see, it takes us a bit longer to recover, but still in 400 milliseconds we recover almost all the throughput on the remaining machines that we had before. And the reason why it takes us longer is, of course, that we have to recover a lot more transactions. In this particular case, we recover 130,000 transactions in about 400 milliseconds. Okay? So to conclude, I'm just going to briefly recap. So I presented farm transactions, which are tailored to hardware in modern data centers. In order to achieve good performance, we use one-sided RDMA operations. We design protocols to have low message counts and also use parallelism as much as we can. We achieve very high performance and high availability. And just one more slide to basically tell you what next sort of for farm as the project, but also what next is interesting, or what else I think is interesting to look into as research challenges and problems. So basically, we are currently working on putting farm in production. This is an ongoing incubation effort, and I'm hoping to show a demo of a working system on Thursday. We're basically working on building a graph store, which is one of the interesting target applications that the farm was built to support. And I can tell you that this is a really great experience because this sort of allows us to go all the way from looking at this new hardware and thinking what should we do, how we should use this hardware in the best possible way, and hopefully all the way to the production and actually seeing things running actual production workloads. And I'm only going to talk briefly about two very interesting hardware trends you might be familiar with already that are going to create many interesting challenges and opportunities for doing great research. One is non-volatile memory. Obviously, we know that Intel is announcing this 3D cross point, which is going to have a lot higher capacity than DRAM. Is going to be non-volatile, so the contents of memory don't go away when the power goes away, but it is slower. And using this in the right way is going to be quite challenging and interesting. The natural questions are how to design various types of data stores, or even how to design storage for these future systems. So this is going to impact the way we build systems quite significantly. And then another very interesting thing is this chip integration and specialization. So we are seeing more functionality being put with the CPUs, like for instance integrating the NICs, or building special instructions with putting special instructions in the CPUs. An interesting twist to this is if we can actually use FPGAs either integrated with the CPUs or integrated with other components in the system. For instance, Microsoft has this Catapult system that is basically integrating FPGAs with the network. And then obviously this creates very interesting challenges and opportunities on thinking where to put computation, or what kind of computation to put on NICs, on memory storage in the CPUs, and what to do where. Basically rethinking how we run our workloads in the future. Okay, thank you, and I can take more questions.
So you showed the graph when you fail 18 machines.
Yes, yes.
So how is the system able to achieve the same throughput as before? I mean,
Yeah, so the graph is actually showing the throughput of the machine even before the failure of only the machines that that survived the failure. This is essentially the sort of maybe the artifact of our test harness that basically collects the throughput of only the machines that are there at the end of the experiment.
okay.
Yeah.
So people probably ask this every time you give this talk. How does your whole system relate to this cap theorem, and how does the system deal with partitions, or does it?
Oh well, when there are partitions, if there are not enough machines to keep processing, we basically stop. We stop being available if you lose too many machines. So in the case when we basically what the system does is another thing that the configuration manager does is it's responsible for allocating regions and placing them on all the machines in the system. And when there are failures, it is going to know whether we lost all replicas of some of data. And at that point, we basically wait for the machines to rejoin the system, and we are not available in that period of time. So very easily. Okay. If there are no more questions, thanks, and hope to see you on Thursday.